Partition of energy. The Earth is made of various rock formations with different physical properties in contact with each other. For example, petroleum traps show contacts between oil and water-filled sand, between shale and sand, between shale and water, and more. Four classic examples of interfaces are the air-solid interface, which separates the atmosphere and the Earth, the air-water interface, which separates the atmosphere and the sea, the water-solid interface, which separates the sea and the Earth, and the solid-solid interface. What happens when waves encounter obstructions like these interfaces is the foundation of seismic imaging. As we discussed in one of the introductory lectures, the notion of P and S waves, the notion of reflection and transmissions, refractions, the notion of free surface, diffraction, and anisotropy are central in the understanding of wave propagation, seismic data, and the linkage between wave propagation to seismic data. If you understand these 5 concepts and learn to use it in conjunction, then you will be able to explain any complex phenomena associated with seismic wave propagation and your seismic data, because complex cases are just mixtures of these 5 concepts. We have discussed the notions of P and S waves, and to a lesser extent, anisotropy, in the previous lectures. We will discuss anisotropy further in future lectures. Our first objective now is to familiarize you with the notions of reflection, refraction, transmission, and diffraction in the context of wave propagation. We will also introduce the notions of rays, Snell's law, Zaprit's equations, and travel time equations. These notions are integral parts of any description of reflection, refraction, transmission, and diffraction. Here are some of the key outcomes. Familiarize yourself with the notion of rays and Fermat's and Huygens principles. Understanding the differences between PP reflections, PS reflections, SP reflections, and SS reflections. Understanding the difference between post-critical reflection and pre-critical reflection. Understanding the difference between reflection and refraction surveys. Understanding the differences between reflections and diffraction. Understanding again the differences between body waves and surface waves. Understanding again the differences between Love rays and Rayleigh waves. Familiarize yourself with the boundary conditions between 2 interfaces, including the air-water and air-solid interfaces. Let's start by recalling the basic notion of rays and the Huygens and Fermat principles before introducing the concept of reflections, transmission, refractions, and so on. A wavefront represents a set of particles, or points, which undergo similar motions at a given instant in time. A snapshot of wave propagation at a specific time represents a wavefront. The two semicircles in this illustration represent two wavefronts. Let's repeat this. A snapshot of wave propagation at a specific time represents a wavefront. The two semicircles in this illustration represent two wavefronts. Rays are defined as lines normal to the wavefront. That is, they point in the direction of propagation. This figure shows examples of straight rays. These rays are the solid straight line in this figure. In general, rays are straight lines in homogeneous, isotropic, elastic media. Let's repeat this due to its importance. Rays are defined as lines normal to the wavefront. That is, they point in the direction of propagation. This figure shows examples of straight rays. These rays are the solid straight line in this figure. In general, rays are straight lines in homogeneous, isotropic, elastic media. Again, notice that the rays are straight lines when the medium is homogeneous, and they can take any arbitrary form when the medium is heterogeneous. Rays provide a convenient way of schematizing events in seismic data because they allow us to track a wavefront. Here are examples of bending in a heterogeneous medium. On your left, we have wavefronts, that is, travel time contours in a heterogeneous medium. They are superimposed on the velocity model. Each black line represents a wavefront. Notice that the wavefronts are not circular here because we have a heterogeneous medium. The departure from circular wavefronts is due to the fact that waves travel faster in regions with high velocity, or red regions, and slower in regions with low velocity, or blue regions. Again, each wavefront is just a snapshot of wave propagation, but with the distinct difference that the amplitudes of its wavefronts are constant. On your right, we have rays, that is, lines normal to the wavefronts, through a heterogeneous medium. They are superimposed on the velocity model. For an inhomogeneous medium, the shape of wavefronts can change with time. Therefore, since the rays are normal to the wavefronts, their paths will also change with time. We have bending rays. Notice the rays bend inwards in regions with low velocity, the blue regions, and outwards in regions with high velocity, the red regions. Huygens' principle states that all points on a wavefront can be considered as point sources for the generation of secondary wavelets. The point on the wavefront at T0 represent the secondary sources. The semicircles around these points represent the wavefront. Let's repeat this. Huygens' principle states that all points on a wavefront can be considered as point sources for the generation of secondary wavelets. The point on the wavefront at T0 represents the secondary sources. The semicircles around these points represent the wavefront. After a time, T0, the new position of the wavefront is the surface envelope tangent to these wavelengths, as illustrated here. If we apply this principle to the wavefront at time t0, as shown here, we can construct the wavefront at time t0 plus delta t. For the sake of simplicity, we display only the wavefront of P waves in this example, as similar illustrations for S waves can be repeated. The procedure for predicting the wavefront at time t0 plus delta t can be summarized as follows. We select a few point sources on the initial wavefront. We calculate the radius of the secondary wavelets based on the velocity of the medium and elapsed time delta t. And we construct these wavelets and draw a surface tangent to them. This procedure yields the wavefront at time t0 plus delta t. Again, for an inhomogeneous medium, that is, a heterogeneous medium, the shape and/or direction of wavefronts can change with time. Therefore, since the rays are normal to the wavefronts, their paths will also change with time. Fermat's principle, also known as the principle of stationary time, allows us to predict the ray path under these circumstances. Fermat's principle states that the wave path between any two fixed points is the one along which the time of travel is the extremum of all possible paths. For example, the ray which follows a minimal time path, that is, the path that will allow the wavefront to move from A to B in the shortest amount of time, is an extremum of all possible paths. Let's repeat this. It's very important for the rest of the class that you understand this principle. Fermat's principle states that the wave path between any two fixed points is the one along which the time of travel is the extremum of all possible paths. For example, the ray which follows a minimal time path, that is, the path that will allow the wavefront to move from A to B in the shortest amount of time, is an extremum of all possible paths. Now, let's talk about reflections and transmissions, starting with the fluid-fluid interface. Let's now consider a heterogeneous model consisting of two infinitely homogeneous and isotropic media, separated by a horizontal surface, as illustrated here. This model is also known as a two-half space model, in which each homogeneous medium represents a half space. Assume that an explosive source, as shown here, generates a P wave, which propagates in the top half space. When the wave reaches the interface between the two half spaces, part of its energy returns to the half space from which it came. This process is called reflection. The remaining energy enters the second medium. This process is called transmission. Let's watch. In this figure, the phenomena of reflection and transmission described by the movie are now displayed as snapshots. The symbol I indicates incidence waves. The symbol R indicates reflected waves. And the symbol T indicates transmitted waves. In the top figure here, The phenomena of reflection and transmission are now displayed by the wavefronts. Having superimposed the corresponding ray paths to these wavefronts, we can sometimes abandon the complexity of snapshots and wavefronts to use rays alone, as shown in the bottom figure. Remember that rays are defined as lines normal to the wavefront. That is, they point in the direction of propagation. In the top figure, this line is represented in white. The angle between the incident ray and the normal to the interface is the angle of incidence. We can ask what the relationship of the angle of transmission and the angle of incidence is. In other words, why is the ray path of the transmitted waves different from that of the reflected waves? Snell's law will establish this relationship and others. Consider 2 points, A and B. Although we could draw an infinite number of paths, each coming from A, and after reflection going to B, only one path can actually be taken by the wavefronts for homogeneous half spaces. This path, according to Fermat's principle, is shorter than any other path. It is the path corresponding to the shortest travel time. Let's now use Fermat's principle to derive the relationship between the incident angle and the angle of reflection. We will refer to A as the distance from point A to the interface between the two half spaces, and B as the distance from point C to the interface between the two half spaces. From the Pythagorean theorem, we can determine that the total path from A to the point of reflection of the interface between the two half spaces, and from there to B. This length is highlighted in blue, and the time needed for P waves to travel to this path is given by the top formula. Furthermore, setting the derivative of t with respect to x equal to 0, we arrive at the following expression. Remember that we are taking the derivative of time with respect to x to be 0, because we are looking for the minimal travel time. In other words, finding an extremum corresponds to taking the derivative with a certain time and setting this derivative to 0. We're now going to write the first term as a sine term and the second term as sine also. Here are the specific sine terms. We can see that the sine of the incident angle over the velocity of the top layer is equal to the sine of the reflected angle over the velocity of the top layer. Therefore, the incident angle is equal to the reflected angles. Thus, the path for which the time of travel is shortest is the one for which the angle of incidence equals the angle of reflection. That is what you can see in the ray diagrams. The approach used in determining the relationship between incident and reflected rays can also be used for incident and transmitted rays. When examining this figure, we would like to know the path of the shortest time for a ray traveling from A to C as it passes through an interface separating materials with differing velocities. Consider the P wave velocities VP1 and VP2, above and below the interface respectively. The time it takes for a ray to travel from A to C is given by this formula. Again, we differentiate the travel time with respect to x and set it to 0 because of Fermat's principle. Again, the two terms here are sine terms. The first term is the sine of incident angle, and the second term is the sine of the transmitted angle. We can see that the sine of the incident angle over the velocity of the top layer is equal to the sine of the transmitted angle over the velocity of the bottom layer. Therefore, the incident angle is not equal to the reflected angles. This relationship is commonly referred to as Snell's law. Snell's law was initially obtained empirically. Now it can be proven as a consequence of Huygens Principle or Fermat's Principle. The ray of transmitted wave bends away from the interface normal if VP2 is greater than VP1. The ray of transmitted wave bends toward the interface normal if VP2 is less than VP1. When a transmitted incident angle reaches 90 degrees, the wave is refracted along the interface rather than transmitted into the second half space. Waves are no longer transmitted to the bottom medium from this point. We reach the critical angle. So the critical angle is not possible when the velocity of the top layer is greater than the velocity of the bottom layers, because the transmitted angle can never reach 90 degrees in this case, as illustrated in the previous slide. Snell's law predicts the critical angle from which such refractions occur as the inverse sine of the ratio of the velocity of the top layer over the velocity of the bottom layer. Note that if the incident angle is greater than or equal to the critical angle, then no seismic energy can penetrate into the bottom half space, and it is consequently reflected into the top half space. If the velocity of the bottom layer is less than or equal to the velocity of the top layer, there is no critical angle. When the incident spheroidal wavefront hits the interface at critical angle, a so-called head wave is produced. The head wave travels with the velocity of the bottom layer along the interface and radiates into the top half space where the velocity of the top layer is less than the velocity of the bottom layer. The energy returning into the top half space, as represented in this figure by rays which leave the interface at the critical angle, define a plane wavefront. This plane wavefront is actually the head wave. Because the head wave travels with a velocity higher than the velocity of the top half space in a part of its wave path, it arrives significantly ahead of the spherically spreading direct wave, which travels from the source to the receivers without hitting the interface between the two half spaces. Again, the energy of the head wave is continuously transmitted back into the top half space as it propagates along the interface. Let's now move to reflections, transmissions, and refractions at the solid-solid and fluid-solid interfaces. Up to this point, we have assumed that the S-wave velocities in both half spaces are zero. In other words, these media do not support S-waves. Here, we generalize Snell's law to cases in which S-wave velocities are non-null. Let's now consider two solid half spaces. Assume that the explosive source generates a P wave, which propagates through the top half space. When the wave reaches the interface between the half spaces, it is partitioned into two reflected waves, P and S waves, and two transmitted waves, also P and S waves. Let's watch. The angles of the reflected S wave, phi r, and the transmitted S wave, phi t, are defined in this figure. We have seen in the previous section that when theta t reaches 90 degrees, Snell's law predicts the critical angle from which P wave refractions occur. In the elastic case, a second critical angle can occur when phi t, that is, the angle of transmitted S waves, reaches 90 degrees. Snell's law predicts another critical angle from which such S-wave refractions occur. Note that if the incident angle is greater than or equal to the critical angle associated with S-wave refractions, no S-wave energy can penetrate the second half space, and the incident energy is consequently reflected back into the top half space. Also note that the critical angle associated with P wave is always smaller than the critical angle associated with S waves, because the P wave velocity is always greater than S wave velocity at any given point or in homogeneous media. Furthermore, if the S wave velocity of the bottom half space is less than or equal to the P wave velocity of the top half space, the second critical angle associated with S waves does not occur. Let's now turn to incident S waves. The Snell's law are quite similar, as you can see here. For example, the sine of incident S wave angle over the S wave velocity of the top layer is equal to the sine of the P wave transmitted angle over the P wave velocity of the bottom layer, and so on. Please look carefully at the diagram to understand our description of critical angles here. So for an incident S wave, we can have three critical angles. One angle is associated with refracted P waves in the bottom half space. The second angle is associated with refracted P waves in the top half space. The third angle is associated with refracted S waves in the bottom half space. Note that we have refracted waves here in the top half space because the P wave velocity is always greater than the S wave velocity for a given homogeneous isotropic elastic medium. Please pay attention to the fact that we now have an additional diagram with P wave incident to complement the S wave incident. This will help you to better understand our description of critical angles here. So for an incident S wave, we can have three critical angles. One angle is associated with refracted P waves in the bottom half space. The second angle is associated with refracted P waves in the top half space. The third angle is associated with refracted S waves in the bottom half space. Note that we have refracted waves here in the top half space because the p wave velocity is always greater than the s wave velocity for a given homogeneous isotropic elastic medium. Let me help you to understand this point more. Remember that for an incident p wave, we can have two critical angles only. One angle is associated with refracted p waves in the bottom half space. The second angle is associated with refracted s waves in the bottom half space. We have no refracted waves in the top half space because the p wave velocity is always greater than the s wave velocity for a given homogeneous isotropic elastic medium. Now it's time for a quiz. Determine the number of critical angles at a boundary between two solids for these cases. Here are your answers. This table provides a summary of the number of critical angles as a function of incident wave types and of velocities. As described in the acoustic case earlier, refracted waves, also known as head waves, occur after the critical angle. As the elastic case that we have just described includes several possibilities of critical angles, several head waves are possible at the interface of two half spaces. This figure shows the ray paths of 5 possible head waves for the case of an incident p wave. These head waves are also illustrated in the snapshot plots here. We can see that there are 5 possible head waves with an incident p wave. Actually, 5 head waves is the maximum possible number for an incident p wave for the mathematical proof of this number. 4 are in the upper medium, 1 in the lower medium. This maximum number of 5 head waves is possible only if VP2 is greater than VS2 is greater than VP1 is greater than VS1. Now it's time to revisit the free surfaces, that is, air-water and air-solid interfaces. What is a free surface? Let's start by examining wave propagation through a 3-layer model consisting of air, water, and solids. The air-water interface in this model represents the sea surface. Here are snapshots of wave propagation through this model, with a source in the water. Contrary to the snapshots corresponding to the water-solid interface, we can see that the reflection at the air-water interface is total. Very little energy is transmitted into the atmosphere because the velocity and density of the air are so low in comparison with the velocity and density of water. Although a free surface means contact with a vacuum, the experience clearly shows that the sea surface can be approximated as a free surface. We repeat the experiment shown in previous slides for another 3-layer model, consisting of an air-solid-solid, in which the air-solid interface represents the Earth's surface. This figure shows snapshots of wave propagation through this model, with a source in the first solid layer. Contrary to the solid-solid interface, we can again see that the reflection at the air-solid interface is total. Very little energy is transmitted into the atmosphere because the velocity and density of the air are so low in comparison with the values for the solid. Therefore, we can approximate the Earth's surface as a free surface. Snell's law applies at the free surface as it does at any other surface. For an incident S wave, we also have Snell law between incident waves and reflected P waves. Also, we have Snell law between incident S waves and reflected S waves. Now we have a critical angle, which is refracted P wave, as you can see from this formula, because P wave velocity is always greater than S wave velocity in homogeneous isotropic elastic medium. In other words, we have a critical angle, and therefore we have refracted waves, that is, surface waves. So surface waves are waves which can exist at a horizontal interface between two media, in which at least one must be a solid, which is the case for air-solid interface, but not for air-fluid interface. Let's now consider the case where the interface between two half spaces discontinues. The subsurface contains faults, pinch-outs, unconformities, and more. In such cases, the laws of reflection and refraction are no longer adequate because the energy is diffracted rather than reflected or refracted. Waves do not travel in straight lines when they pass by an obstacle. They don't form sharp shadows. Any change of this kind in the direction of propagation, which is not due to changes in the properties of the medium, that is, anisotropy, is called diffraction. Consider, as an example, a plane wave of infinite extent traveling in a homogeneous material. Three typical secondary wavelets are shown in the top figure. Arrows represent the amplitude and direction of the particle velocity due to the wavelets. These vectors cancel each other in all directions except in the direction of propagation. Consequently, the envelope of the secondary wavelets remain a plane wave. However, if for some reason the wavefront is limited, this mutual cancellation is not complete, and the resulting envelope of the secondary wavelets is no longer a plane because it has a diffraction tail. The phenomena of diffraction is most easily explained by Huygens Principle. It states that if one knows the position of a wavefront at time t, the position of wavefront at time delta t can be determined by treating each point of the original wavefront as a source of secondary waves. The secondary wavelet have centers on the original wavefront. The radius of each wavelet is equal to the propagation velocity multiplied by time interval delta t. The envelope of the secondary wavelet shows the position of the forward wavefront. Let's now turn to wave propagation in 2D media. This figure shows a wave pattern produced at the termination of a reflector. The original down-traveling wavefront is shown here as I and radiates from the source point. The reflected wavefront is shown as R. The reflected wavefront suddenly changes to a wavefront of greater curvature near the end of the model. This wavefront, denoted by D, radiating from the top corner of the broken stratum, is a diffraction. This diffraction, in turn, changes to a wavefront of greater curvature, which is a diffraction from the low corner of the broken stratum. We are now showing the wavefront pattern for a fault model. The reflections from each side of the fault, R1 and R2, end abruptly and become diffractions. Again, it is the limitation of the reflected wavefronts with the resulting lack of wavelet cancellation that causes the diffraction. So finally, let's conclude this first lecture of energy partition at an interface by describing surface waves, which are waves traveling at the air-solid interface, or at the solid-solid interface. Surface waves are waves which can exist at a horizontal interface between two media, in which one must be a solid. Let me emphasize that at least one must be a solid. In other words, there is no surface wave at the air-water interface. For example, there is no surface wave at the atmosphere-sea surface interface. However, there are surface waves at the air-solid interface. For example, there are surface waves at the atmosphere-continental crust interface. There are also surface waves at solid-solid and fluid-solid interfaces. There are two families of surface waves. Surface waves with displacements only in the vertical plane, which are waves that are vertically polarized, and those with displacements only in the horizontal plane, which are waves that are horizontally polarized. Surface waves are generally classified according to the names of their discoverers. At the air-solid or vacuum-solid interface, we have Rayleigh waves, which are vertically polarized waves, and Love waves, which are horizontally polarized waves. To help you distinguish P and S waves, that is, body waves, from Rayleigh and Love waves, let's watch these animations. Strictly speaking, Love waves are not surface waves. They are guided or trapped waves. Love waves are not present at the interface between two half spaces. If, however, a heterogeneous solid layer is bounded by a free surface, Love waves showed that dispersive SH waves will exist. The shear wave velocity in the half space must exceed the shear wave velocity of the above layer. Love waves are one of the major contributions of noise in SH wave reflection data. Special horizontal force sources, which predominantly generate SH waves, as we will discuss in future lectures, have been used on land for characterization and imaging of the shallow subsurface. As we mentioned earlier, there are also surface waves at fluid-solid and solid-solid interfaces. We have Stoneleigh waves at a solid-solid interface and Schultz waves at a fluid-solid interface. In summary, there are several reasons for studying surface waves. First, they are part of the elastic wave field recorded in active seismic experiments, that is, man-made seismic experiments, and passive seismic experiments, for example, earthquakes and volcanic eruptions. Therefore, it is necessary to understand their properties and what distinguishes them from body P and S waves. In a land seismic experiment in which we generate and record waves at the air-solid interface, which is mathematically represented by a vacuum-solid interface, Rayleigh waves, generally known in petroleum seismology as ground roll, are the dominant components of the data. They tend to mask the desired signals. We have now concluded our discussion of Snell's law at the horizontal interface. When we return, we will describe Zaprit's equation and travel time equation at the horizontal interface.